And that tried to set up so that it would be better today, and we should have made a few adjustments in regard to the camera resolutions issue. Tell me if it seems to have helped.
Okay.
Sorry that the doors back there are locked. I've just sent an email to the person who should be able to unlock it. But for the time being, oh, somebody came in. Maybe it already would have worked. Somebody managed to open it. Get in. Good. Okay, assignment 4, which is the first one that will have MATLAB programs that you need to turn in, is online. You will find it on the Sakai site. Like many of the assignments, most of the other assignments for the semester, you will be needing to submit both a report and a MATLAB program. The report is written in, you can submit a PDF or any other form of the text being shown. And it will frequently include pictures, and so you'll need to have some text, and in that you'll submit some example results. And that report will be submitted in Sakai. Okay, but the MATLAB program will be submitted to a Matlab Grader, which will basically be something that takes your program and runs it against some data that we provide that you will not know about, and will grade it as successful or not in terms of whether you get the results intended for the input that we provide. But you have access to the Matlab Grader beforehand, so that you can provide it with your own data and see yourself whether it it succeeds on your inputs. So Andrew Chun here, one of the LAs, is going to now explain how you use the Matlab Grader. So Andrew, go ahead.
Okay. Hey everyone, I'm logged into my account here, as you can see on the screen. If you guys haven't already made a Matlab Grader account, please go ahead and do so as soon as possible and send me the email so that I can sign you guys up for the course so you guys can have access to the grader. So I'll show you guys what it looks like a little bit.
So you sent an announcement on where the grader can be found?
Yes.
Okay, good.
Alright, so this is what it might look like once you enter. I think it's a little bit different for you guys, but general same overview. This is an example. I don't think you guys are able to see this, but as we put up assignments, it'll look something like this. There will be an assignment, and then under each assignment, there will be multiple problems. On each assignment, there'll be multiple problems that you'll need to submit, or maybe it's maybe a larger problem, and we'll break it up into smaller problems so that it's easier for you guys overall. And so for each problem, we'll give a problem summary, and then you guys will have to create your own programs and try to run it, try to submit it with the program. And we'll have our own inputs, like Dr. Kaiser said, and it'll show you whether or not your program matches up with what our program is.
I don't think you're on Zoom.
And
Are you on Zoom?
every assignment,
Are you
will
on
have
Zoom?
unlimited submissions, unlimited submissions for each problem. So that'll be a good help for you guys, so you guys can.
Could you hold up for a moment? I realize that I haven't set my computer to mute and everything, and we're getting recording problems. Hold on. I haven't got on in the first place. Hold on. Give me a moment. I screwed up and never got onto the Zoom. Sorry for the confusion. So many things to set up at the end of class. This one. Okay, go ahead, Andrew.
Okay, so everyone again. So this is the Matlab Grader that you guys will be using to submit your Matlab programs. If you guys haven't already signed up already, make sure you guys do that as soon as possible and email me the email that you guys used to create it. And this is what it might look like for you guys as you enter. Probably the same thing for you guys as students. Okay, and so this is how it's gonna look. You can have assignments on the left. If you click an assignment, it'll show the problems associated with that assignment. And those problems are gonna be like the separate questions in the assignment, or it might be maybe one long question that's broken up into multiple parts to make it easier for you guys. And so as you guys finish the assignments, finish the programs and submit it to the grader, we'll compare it with our program to see if it matches what we're expecting. And if not, it'll tell you if you're wrong or not. And we might have to put like individualized feedback. But regardless, it'll tell you if you're right or wrong. That'll be a big help for you guys as you guys are finishing up your Matlab programs. And this is this Matlab Grader. This Matlab is essentially what the LAs are here to help with. So if you guys are struggling with creating the programs at all, please come to us, to our office hours, or email one of us. All right.
How do they submit their own data?
It says like a submit button. I can't show
You
them
can
because-
use the learner preview to see what our site looks like when you click on the individual problem.
Let me check that there. The learner preview.
Yeah, so where were you, like in the editing, in like the problem edit, if you scroll down to the bottom, there's a learner preview button,
learner preview,
and
yeah.
that'll like show it how we see it.
Oh, okay, thank you. Okay, yeah, perfect. So here's the input where you need to write your function. It'll be easier if you maybe code it locally on your own Matlab, and then just copy and paste the function into here later. And here we'll start you off with just like some comments, maybe just give you some hints or just explain the variables that we need in the function. And then to run it, we'll call your program with our own input images. You guys won't be able to see that, but that's like our input to check if your program matches with our program, our expected program.
But during practice time, they need to be able to submit their own data, and that's what I'm asking you about.
They're not submitting their own data on here. They can run it on their local programs with their own data. But when it's submitted here, it runs our.
Okay, so
our
my
data.
mistake. I thought they could use the grader to. Okay, fine.
And yeah, there's a submit button down here, and also some pre-tests that we might have set up or not. And yeah, that's pretty much how you guys will be submitting your programs throughout the semester.
Question. I don't see the assignment in there.
Yeah, this shouldn't be visible for you guys. It was just kind of like something I set up last night. But
You don't see it on the Sakai side?
No, on the Matlab Grader. Like, I
It's-
see the course, but it doesn't show any
Okay,
assignment.
you still have to set it up to receive assignment 4.
Yeah.
That has not yet been done, is that correct?
yeah, I haven't set up the assignment
Okay,
for this.
just wanna
is
make
like,
sure.
Okay, but please do set it up, because there's some people will be happily ahead of time
Mhm.
and will want to submit it right away.
Yeah. Any more questions about the grader?
Okay, so why don't you get that off my screen and we'll get some other windows up. Okay, so what you see here, there is a course, calendar. Andrew, would you please add to the calendar my office hours and class time,
Okay.
okay? But
Class time's already in there, but I'll add your office hours.
Okay, fine. Anyway, as you will see, the office hours in each week have been chosen by the LAs. All of them but this one here are in the 9 to 5 noon time, and those will take place in Citizen 284. That's the conference room outside my office, okay? Well, I'm organized, because you don't have keys to get up onto the second floor, beyond the end of the workday. That room is not good for you for this evening office hour. Wednesday And so I've asked for an assignment of space for that, right? And we'll be getting an announcement to you on where that is, okay? So and remind you that the LA office hours are for all these mechanics, including how to code in Matlab if you have problems with that. Any questions about that? As far as my office hours, I'm planning to be here in the building on Mondays, Tuesdays, and Thursdays normally, not on Wednesdays and Fridays. And so my Tuesday office hour today, for example, is in my office, which is in that corner, in the Citizen Hall building, on the 2 level. However, because I'm not going to be here on Fridays, we're going to do Friday office hours virtual. Okay? Sorry for the complication. Trying to keep a little bit healthy. Anyway, moreover, this week there's a proposal, PhD dissertation proposal meeting for one of my advisees on Friday that conflicts with the office hours, so I'm going to have to miss my office hour this Friday. If anybody has questions during, that they need answered towards the end of this week from me, I am happy for you to send me an email. We'll set up a one-on-one appointment. Okay? I already talked about this. Assignment number 4 has two things to turn in. Are there any questions on anything? Substance, administration? Nothing? Fine. Okay. So let me put this down. And put okay, so let me remind you where we were at. We were trying to figure out a good set of basis images for and a good set, we were trying to get a good set, and a good set should have the property that you only needed few basis images before the coefficients were essentially 0 for pretty much any image that you want to deal with. And also you wanted to be able to have shift invariant linear operators be able to be done fast. And I started to tell you that the sinusoids do just that. Put another way, they are the Eigen Images of shift invariant linear operators. Meaning that in order to apply a shift invariant linear operator, you can represent an image as a linear combination of the sinusoidal basis images. And once you have that, all you need to do is to multiply the respective coefficients of the Eigen Images by the eigenvalues associated with that operator. We call those the lambda sub k's for the kth eigenimage. And then recompose the image with coefficients no longer a sub k, but a sub k lambda sub k. Questions about how that works? Now, so I had said that the eigenimages are sinusoids, and these are two possible sets of eigenimages that you see here. Yeah.
Can you screen share the slides on Zoom?
Say again?
Screen share the slides on Zoom.
Oh. You guys guy's gonna come here and help me set up every time. Let's see, screen share. Slides. That do it, Alan?
Yep.
Unfortunately, one member of the class has to be remote because roommate got infected with COVID-19. Anyway, that okay now, Alan? Okay, so these are just 64 of the Eigen Images on the left that you might use, a particular set. The set on the right is a different set. But I want to point out what the properties of those images are. First of all, we have X frequency sinusoids, and we have Y frequency sinusoids. So we have 0 frequency, which is just constant. Cosine of 0 is 1, right? We have something with a cycle in X that is the whole width of the eigenimage. Each one of these squares is an eigenimage, a sinusoidal eigenimage. So, right, so this is a period of the cosine, which is the full width of the image. And then we see one that has a higher frequency, and yet a higher frequency, and yet a higher frequency, and yet a higher frequency. So these are all organized by frequency, yep? Higher and higher frequencies in X. This way is higher and higher frequencies in Y, right? So again, in Y, you get a cosine with a full period, and then the period is a third and a quarter and a fifth, and so on, right? A fifth of the image width. And then all the rest are simply products of the other two. So this one is a product of basically this one and that one. Right? It's got an X frequency and a Y frequency. That is the period is the full image width, and so on. Okay, so you get the general idea, I hope. And okay, so why would these, besides being good for convolution, because of the fact that you can just multiply everything by the eigenvalues once you've decomposed an image into those basis images, why would it be good for only needing a few of these basis images to represent an arbitrary image? Well, if you think about this way these frequencies go, the level of detail that they capture is smaller and smaller and smaller as you go left to right or top to bottom. Right? A sinusoid that goes up and down very fast is really good for capturing image data that has small details. And one that goes up and down much less fast, like the ones on the left or in the top, depending on whether you're going in X and Y, is great for telling things of roughly the size of the half wavelength of the object. So if I wanted to get a result which is good for finding doors, double doors at the back, I'd want something that has a half period that's about that width. But if I wanted something that was really good for representing faces, yeah, that your faces are smaller than the doors, I'd want a higher frequency, a shorter wavelength. And if I want something that's really good for looking at the wires down here, I'd want even higher frequency, yet shorter wavelength. This idea of level of detail. Point is that after a little while, going in that direction, you're interested in and they'd be good for sensing really, really fine details, most of which either you're not interested in or will be hidden by the fact that they're dominated by image intensity noise. And we will see how image intensity noise corrupts the image information at higher frequencies anyhow, and therefore we don't particularly want to represent what's mostly noise anyway, and that's why the limited number of these basis images by frequency will do the job for us. Okay? Yeah, question?
I have a question, sir. Why is the sign Eigen Images, why are they kind of like shorter or smaller overall? It seems like they're like a little sharper. Is there any reason for that? Or like the individual little Eigen Images are kind of smaller?
Good question, and I didn't prepare these slides, so I don't know why that's the case. Sorry.
I didn't know if there's any reason.
No, indeed, it's a good question, but there isn't really a difference. I mean, it's just sort of the way in which they were copied over from some other sources. Okay, so looks like the sinusoids are going to be a good bet. And by the way, you will see that it's not coincidental that they happen to be organized by scale, by the size to which they're sensitive, right? Right. And that will come from something we'll see shortly about the orthogonality of these Eigen images. Okay, so let's get okay. So so far we have seen that a sinusoid at frequency nu has two terms with real coefficients, cosine 2 pi nu x and sine 2 pi nu x are, if you will, a sinusoid at just two different phases, and you have a coefficient of the sine and a coefficient of the cosine, two coefficients. If the data consists of m entries, in our case for an image m will be n squared for an n by n image, what we're trying to do is to represent these n squared pixel values, or in the case of, let's say 3D, where it's m is n by n by n, as n cubed. You're n cubed, but if you have m and you have two coefficients per frequency, then we're going to need basically m over 2 coefficients to fully represent everything. Okay? This is a basic property of vector spaces. Images, in fact, form a vector space, that the number of scalar values that you need to represent things fully, m, in any other representation will require m coefficients. Right? Some of them, those coefficients can be very small, almost zero, or even equal to zero for special images. But you need exactly the same number of coefficients. And since we're going to need 2 for each frequency, we're going to need roughly m over 2 frequencies. Right? But we've also seen in this slide that you can rewrite this as in terms of one coefficient, which is a squared plus b squared to the half, a magnitude, and a phase phi given by tan inverse the ratio b over a. Put another way, one number here, a magnitude for every frequency, and one number here for the phase. Again, 2 per frequency. So 2 alternative ways to represent the coefficients of the image data at that frequency. Okay? You can either do a pair like so, or a pair of magnitude and phase. And in both cases, you're going to still you have a pair, and you need a roughly m over 2. You'll see why roughly in a minute. There are a couple of special frequencies where you only get one, and so you need a m over 2 plus 1 frequencies to get the full m coefficients. But there's a third way to understand these basis images, and that has to do with understanding each one of these as complex. Okay, basically the cosine term is the real part and the sine term is the imaginary part. Okay, and so we're going to talk a little bit about understanding it as complex numbers, because that's the third way. So, there is a function, you have all seen the function e to the x. And I'll remind you that e to the x has a Taylor series, which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed 3 factorial plus so on, right? That was in your calculus course somewhere. And if you will purely algebraically write x as e to the I theta, x as I theta, what we're going to get from this series is 1 plus I theta over 1 factorial plus I squared x squared over 2 factorial, theta squared, sorry. But I squared is minus 1. Right? The imaginary constant I, when you square it, is minus 1. So you get minus theta squared over 2 factorial. Then we're going to get I cubed, theta cubed, over 3 factorial. But theta, I cubed is I squared times I squared is minus 1. Okay, and so this is going to become minus I. Then we're going to get theta 4 over 4 factorial, and I to the 4th. But I to the 4th is minus 1 squared, which is 1. So on. And then we're going to get I to the 5th, theta to the 5th over 5 factorial. But I to the 5th is I to the 4th times I, and I to the 4th is 1. Okay, the main point here is that the odd terms have an I in them and produce a series, imaginary series, which has theta over 1 factorial and theta cubed minus theta cubed over 3 factorial and plus theta to the 5th over 5 factorial. And the Taylor, that is the Taylor series for the sine function. So the imaginary part is just sine theta. And the non-imaginary part, 1 minus theta squared over 2 squared plus theta 4th over 4, is just cosine theta. Put another way, notice what I got here. E to the I, summarizing, e to the I theta encodes a cosine function in its real part and a sine function in its imaginary part. Right? But cosine theta and sine theta are just the properties of the points on the unit circle. So if you look at the unit circle at angle phi, okay, I called it theta over here, sorry. You see that the point on the unit circle has in its horizontal coordinate the value cosine theta, and in its vertical coordinate sine theta. So if you think of the real line as the horizontal coordinate and the vertical line as the imaginary coordinate, you see that all we're doing here is representing each frequency term, that is, say, the pair cosine theta sine theta, as a point on the unit circle, as a direction on the unit circle in complex domain. Okay? So, if we can understand e to the I, or plus or minus I, doesn't matter, 2 pi x as a cosine and a sine, then if we multiply that by, I'll call it A sub nu, and if we let A sub nu be complex, we're going to be just fine. Right? We get two numbers, a real part of A sub nu, an imaginary part of A sub nu. Those are the two coefficients of the term at frequency nu. Okay. To make a long, yeah.
Could we alternatively have raised e to the I times 2 pi nu x plus or minus some phase shift? So
We
that
could
we
have, but
just
that's
do-
sort of redundant.
Okay.
The point is that now you would have four numbers.
Well, then wouldn't we not need a complex coefficient? We could just do a real coefficient.
I guess that, I'd have to think that through. Since that's not one, it's possible that that would work. Okay? But in any case, that's not what is normally done. What is normally done is this way is a complex coefficient of the complex sinusoid, the complexly represented sinusoid at frequency nu.
Okay.
Yeah, good, very good questions. Worth, if you want to take that as an exercise, we could work that out. Okay. So, make a long story short, there are three ways to understand sinusoids at frequency nu, with a sine term and a cosine term, each with its own coefficient, each with its own real coefficient, as a magnitude and a phase for each frequency, and as a complex coefficient of exponentials with an imaginary exponent. Frequency nu. Okay, for this course, I'm making life easy for you. Right? We're going to be sticking to this when you actually compute the magnitude phase version. But in order to understand what's going on underneath the hood, we're going to need to talk about 1 and 3, and especially number 3. Okay, and so that the next part of this lecture is going to be essentially understanding how things go in this complex, with regard to this complex representation. The next thing to know is that the nus that we're going to need are going to be integers over n, where n is the size of for an n by n image. Or in the case of a one-dimensional image, a signal, n is the number of discrete positions, if you will, pixels, in that one-dimensional image. So you're going to get j equals 0, 1, 2, up to n over 2, if you will. let's be a little bit careful. First of all, if you had j equals 0, 1, and 2, what is sine of 2 pi 0 x? That's for j equals 0, right? 0 over n is 0. What's sine of 0? It's 0. It's a 0 image. That doesn't make a valid basis image. Right? The sine term at 0 frequency is all zeros. You can't contribute any basis coefficient to that one. Right? Okay. What about sine of 2 pi n over 2x, where x goes from 0 to that's sine of pi, the 2's cancel, of n pi times an integer, sine of some multiple of pi. 0. Okay, so two of the sine functions don't contribute. So you don't quite have enough coefficients. And that's why I'm going to get n over 2 plus 1. 0 to n over 2, because I have one coefficient at 0, it's only real, and at n over 2, and all the rest have pairs, a complex pair, or equivalently a magnitude and a phase pair. Okay? Okay, so let's look what's going on here. Okay, so what we're going to want to do is e to the minus I 2 pi nu x as basis images, but with nu's being multiples of 1 over n, where n is the number of x, is the number of entries if you're going only in the x direction. So far I'm talking about one-dimensional signals that only have an x coordinate. They're functions of some signal which is a function of x. So our input image looks like the image and x, and the input image is some function like that has values at 0, 1, 2, up to n minus 1. Okay, in a moment we're going to talk about what happens in an image when you have two-dimensional images or three-dimensional images, but for now we're just talking about one-dimensional images. Okay? If we look at what happens in 1D, what we're going to do is try and represent the image as a linear combination of coefficients of these one-dimensional images. But now you'll notice that I have let the frequencies be possibly negative as well as positive. They go from minus n over 2 plus 1 to n over 2. Right? So I can have a positive frequency, nu, or a negative frequency, nu. Cosine is independent of the sine, because cosine of minus theta and cosine of theta are the same. But sine, the sine of theta and the sine of minus theta have opposite signs. Right? Something's wrong. How many coefficients do I have if I let my frequencies actually go from negative to positive frequencies. I've got roughly n frequencies, nk values, and each one of them is complex. 2. So now I got 2 n coefficients. What's wrong? How many pixels are there? N. I got 2 n coefficients. Oh, no fair. Can't possibly be. You need exactly n, and we got 2n. There must be a redundancy here. And sure enough, there is. And I'm not going to take you through this algebra. You can work it out yourself. It's some algebraic stuff. But the conclusion turns out to be that in order for your image data to be real, a sub minus k and a sub k need to be the same as they're just complex conjugates of each other. You understand it? The complex conjugate of a plus ib is star means complex is a minus ib. Right. Okay, so the point is that for the one-dimensional Taylor series, the a sub minus k's are just copies of a sub k with the sign of the imaginary term swapped. So there really are only n basic images, basic coefficients. They're ones for positive k, and the negative ones, yeah, they're there, but they're just copies of the positive ones with their sign switched, the imaginary part made minus. Because a0 and an of 2 have no sign terms, their coefficients have to be real only. Right? Because otherwise you'd be multiplying something at that frequency, you'd be having an imaginary component, and real data has no imaginary components. The data itself is real. So what we end up with is that the zero frequency and the n over 2 index, which is frequency a half, n over 2 over n, have real coefficients, and they're just a0, this guy is times 1, and a sub n over 2, that guy is also 1. So you get a sub 0 times cosine 0 plus a of n over 2 times cosine pi x. So those two terms don't follow the complex conjugate rule, if you will. They're just real, the a sub 0 and the a sub n over 2. And all the rest do follow the complex conjugate rule, where you have exactly complex coefficients of the positive frequencies, and the negative frequencies get complex conjugate coefficients of the positive frequency coefficients. Okay? Okay, fine. One dimension, already complicated, but now we're going to go for 2 dimensions and 3 dimensions. Okay? This is just a repeat of what I said last time, except that it's put in terms of the basis functions cosine terms, because the sine terms with this complex conjugate relationship, when you combine the positive and negative frequencies, you can say I get pure cosine terms. And so in amplitude and phase setup, and there's a bunch of algebra here that shows this, we see that if the a sub k's are complex, and if A plus IB is A squared plus B squared to the half, right? Then you end up with a cosine version with phases. And the coefficients of the cosines are the magnitudes of the complex AKs, with a phase defined by the ratio between the imaginary part and the real part of AK. Right, so the real part of A plus IB, real part of A plus IB is A, and the imaginary part of A plus IB is B. Okay, so, make a long story short, this complex conjugate arrangement ends up meaning that you can think of things as cosines with phases. Instead, so magnitudes and phases rather than complex coefficients. And the complex coefficients are related to the magnitude and phase coefficients by this relationship. You get twice times the magnitude of the complex coefficient as the magnitude term, and you get a phase that is a phase that is the tan inverse of this ratio. And so the whole business turns out to be a real A0, a real A n over 2, just those that were the complex ones, and all the magnitudes are twice the magnitude of the corresponding complex ones for the frequencies with index other than 0 or n over 2. So we get n over 2 plus n over 2 minus 2 plus 2 coefficients in this cosine setup. And notice that this runs from only positive index. Okay. It's a pain, it's complex. Not in the sense of imaginary and real, it's complicated. But it's not conceptually too difficult. Okay, fine. What about m dimensions? Well, it helps to understand what goes on in m dimensions via the exponential form. When you multiply two exponentials together, the product of the two produces something that is a single exponential with the exponents added. Right, and so what we're going to do is play the game of letting A encode frequencies in X, and the B encode frequencies in Y. Which is just going to say that the basis images are going to be the product of basis images purely X and basis images purely Y, and they're going to be multiplied by each other. And that's what we saw in this picture there where we had X frequencies going that way and Y frequencies going that way, and the guys at frequency J in one of the dimensions and K in the other one is going to simply be the basis function, which is frequency e to the X frequency J times e to the Y frequency K. Okay, so now for images, the bases are simply going to be the product of two one-dimensional bases, one set in X and one set in Y. And so all the coefficients that we talked about before that are going to go from 0 to n over 2 in the cosine form, or from minus n over 2 plus 2, but with some kind of a relation between the that make you have half because of complex conjugacy, are going to work just fine. Right? We're just going to have our basis images. Another way of saying this is we can analyze each row of the image in terms of its X frequencies, and we get a bunch of X frequencies for every row. And then we take the result and we're going to separately take those analyses and figure out what they are in Y frequencies. Okay, so we're going to be able to do what's called separable operation. First, pure X operation, and then on the result, pure Y operation. Right? Okay, so the sinusoids now for, let's say, two-dimensional images are going to be e to the 2 pi minus I 2 pi times nu sub x plus nu sub y. All right, it's going to have an X frequency, nu sub X, and a Y frequency, nu sub Y. Okay, and those are, of course, according to this relationship, the same as e to the minus I 2 pi nu sub x times e to the minus I 2 pi nu sub y. Product of two of the one-dimensional basis functions. Okay? Okay, so these separable basis functions are these one-dimensional sinusoids. And the guy who invented all this is a Frenchman named Fourier. And so these sinusoidal basis functions go under the name Fourier Analysis. Okay? The word Fourier transform simply means figuring out what the coefficients are of these frequencies. Okay? So to go from an image I to the A array, the coefficients, that transform is called the Fourier transform, or specifically for us, where our inputs are discrete, integer-valued images, this transform is called the discrete Fourier transform. It's just the mapping from the images to the coefficients that we've been talking about during this whole lecture. Right? And you will find a DFT program in lots of places. But in particular, we're providing you with one. Okay, and it computes these coefficients in the magnitude phase form. Right? So a magnitude and a phase for every frequency. Except be careful, the zero frequency is a real number, and the n over 2 frequency coefficient is a real number. And so those phases, the phase of 0 gives you cosine of 0, which is a positive number, and the phase of pi gives you a corresponding -1 value. And so 0 means a positive magnitude, if you will, a positive coefficient will be understood to have phase 0, and a negative coefficient will be understood to have phase pi. Okay. So what we've said is that the Eigen condition, because all these sinusoids are eigen, in some sense, Eigen images, you have, if I have an input image, and it has complex coefficients e to the in, e to the input, not e to the, capital E sub input, then after applying a shift invariant linear operator, we're going to have an E out, because the result image is also expanded, and the ratio between E out and E in will be the eigenvalues. And these eigenvalues themselves can be complex, have two parts, a real part and an imaginary part. Okay, the ratio of two complex numbers is a single complex number with a real and imaginary part. Now we come to that condition that gives you half. You remember in one dimension it was that for positive frequencies the corresponding coefficient at negative frequency had to be the complex conjugate of the coefficient at the positive frequency. But now we have frequencies that are pairs. We have the x frequency and the y frequency. So we have a nu sub x, nu sub y pair, or if these guys are indexed by j, okay, so in other words, the frequencies are 2 pi j over n x, and these guys are by k, so they are 2 pi k over n x, or n is the width of the image. It's an n by n image, I'm assuming. If you get rectangular images, you can still do it. It's just that the width in x and the width in y will be different. Okay, and so if I think of this pair, j over n, k over n, as a k underline, right, as a pair, as a tuple, a duple, then it turns out that, well, the same algebra that we did before turns out to be that a sub minus kj, or jk, is the complex conjugate, sorry, a sub jk of a sub minus j minus k. Put another way, if I let my frequencies in x go from minus n over 2 plus 1 to n over 2 here, and from minus n over 2 plus 1 to n over 2 here, this guy that has positive j, positive of the x one, that was j, yeah, is also going to be complex conjugate of this one. These two are complex conjugates of each other. And this guy that has negative j, but positive k, minus it's going to be positive j and negative k, and so these two are going to be complex conjugates of each other. Okay, so again we have the twice as, only half as many separate coefficients, if you will. But instead of being straight complex conjugate, it's the guys with negative frequencies, guys with both positive frequencies, and the guys with both negative frequencies are complex conjugates of each other. And these guys with one frequency positive and the other one negative are complex conjugates, but when the first one's negative and the other one's positive. Okay, pain in the rear, but the upshot is that if I only give you the top half, the bottom half is fully specified, with the exception of the special places, which are zeros, which are the 0 and n/2 frequencies of one of them. And it also turns out that something special goes on here and here, with the 0 frequency in y and the 0 frequency in x. And so what ends up happening is, in your program, you can understand what is going to be produced as a magnitude and a phase for every frequency that's green, and a magnitude only for the bars and the dots, because those frequencies 0 and half, n/2/n, are going to have only magnitudes of the phase serial numbers. The phase is known as 0 or pi. They're plus or minus 1. It's a funny kind of magnitude. It's really not a magnitude, because if the magnitude's negative, you wouldn't call it a magnitude. But we're going to let, at those places, let the magnitudes be negative. Okay. If you think that's painful, we get one more set of pain to communicate. But before I do, I want to make a very important point, which is indicated in this slide. We've been dealing with image arrays, right? They are an n by n array. But we're going to use the term matrix for something that's an operator, that applied to vectors or applied to images. And images don't apply to images, they are images. And therefore we're going to not call an image a matrix, despite the fact that the people who wrote Matlab screwed up and called them matrices, Matlab. Right? They're arrays, excuse me. They are arrays, all right, but they're not matrices. Matrices are also arrays, right? They are a rectangular array of numbers, but they act as operators. Okay? The array of matrix elements, you will see, is one way of representing a shift invariant linear operator. In fact, any linear operator, whether it's shift invariant or not, will be able to be understood as a matrix multiplication. So these matrices associated with operators are going to be could be thought of as arrays. But for us, we've seen image arrays, but we've also seen these coefficient arrays, a magnitude array and a phase array. Two images. Not image, yeah, two images, two arrays. And those aren't matrices either. They're arrays. They're listing of all the coefficients of the associated breakdown of an image in terms of eigen images. Okay? So we have arrays of the basic image data. We have arrays of the coefficients of the basis images. One for the magnitude, one for the magnitude, one for the phase, or alternatively, a single array with 2 elements per entry, which is a complex number. And wait a second, we also have these multipliers, these eigenvalues associated with a particular operator. Right? Just to remind you that any shift invariant linear operator is going to have an associated set of lambda sub k's. We're going to see how to get that, those eigenvalue. But that's also an array. It can be understood in the same way as before, as what we've talked about for the images, as a real part and an imaginary part, complex number, or we can understand it as a magnitude multiplier and a phase shift. And that's what we're going to be doing, having a magnitude multiplier, which is basically, for the imaginary version, just the magnitude. And we're going to have a phase shift associated with multiplying by lambda sub k, which is going to be the imaginary part of lambda k divided by the real part of lambda k, when these are understood as complex numbers. Okay, so now our shift invariant linear operators, we're going to have a magnitude multiplier array for every frequency and a phase shift. We're going to modify the phase by adding that phase shift to the other phase, to the phase. Anyway, the point is that that's another array. Actually, a pair of arrays: the magnitude multiplier array and the phase shift array at every frequency. And because all this is going to be the same as, it's got to have ultimately an effect that doesn't produce any imaginary terms in the result, because we're going to end up with real images. We're going to have the same complex conjugate arrangements that we saw here for the lambda arrays. So I'll call it the, if you think of the lambda as complex, then you have for the lambda arrays the same deal, where the doubling up happens crosswise. In 3D, it gets even more harder to keep straight, but it's still the same story. K is now going to be a 3-tuple, an X frequency, a Y frequency, and a Z frequency. And the doubling up is going to be minus 1 3-tuple. It has the same values except for complex conjugation as minus that 3-tuple. notice that these lambda arrays, because of the fact that these are eigen images, these sinusoids, once you get things in these over here into the frequency domain, we say, in other words, once we've computed the coefficients, the magnitudes and the phases, we're going to combine the two element by element. That is to say, the k underlined element of the lambda array and the a underlined element of the image after the DFT, after you computed its coefficients, simply get multiplied together. Okay, element by element. And so the application, this eigen application, is going to be an element by element application over on the in the frequency domain. Over when we have coefficients, lambda k, and coefficients a sub k, with both the k's are underlined. And for a particular k, you only multiply by the coefficient at the other one. There's no crosstalk. That's the lovely deal of going over into frequency domain, is that you only have to do this multiplication. Okay, so this is the last slide of today's lecture. We know that the basis images we want are going to be, if we're going to do shift invariant linear operators, are these sinusoidal images. There exists a program that you put in an image and it computes the corresponding coefficients. It's called the DFT program. And it turns out that that same program can produce the so-called inverse DFT that recomposes an image from its coefficients. So it turns out it's just a parameter, it's a toggle for the same program, whether it goes DFT or whether it goes inverse DFT. It turns out that, yeah, all those exponents change sign. E to the a turns into e to the minus a, but other than that, the whole business is the same when you're doing the inverse DFT. So the single program with the toggle gives you either DFT or the DFT inverse. So the way we're going to apply shift invariant linear operators is we use the DFT to go over. We then multiply new coefficients by multiplying each one of the coefficients by the corresponding lambdas. And then we apply DFT inverse to the result. And we've applied the shift invariant linear operator. We're going to see an alternative way of computing this, which stays over in the space domain, does everything in space. And we're going to see that it's way less efficient to do it that way than this way. This way, it turns out it's dominated by the time to do the DFT, and it turns out that the DFT for an image with m entries takes order m log m time, whereas the other takes order m squared time. And m's a really big number, and log m is, like 10 or 20, but n is 1,000 or 2,000, right, or million. Way faster to go over to the frequency domain and do shift invariant linear operator calculation that way. Okay, so there's been a whole lot of detail. I have made in bold the part that you should know, and the stuff that's not in bold this is for the algebra, the array. Sorry, for the slides that have all this algebra on them. The algebra itself, you should look at and make sure you can follow it, but you don't have to learn it. but the stuff that's in bold on those slides is the result, and you really do have to know that. Okay? Okay, so I will see you on Thursday. Anybody who has questions, feel free to come up and ask them now. Or see me at my office hour this afternoon, which I can never keep my calendar straight. I think it's 2:30.